Today I'm going to talk about imputation. So imputation is incredibly powerful, and it's very important. Like I've done in previous weeks, though, I'm going to start with examples of bad math. So yeah, I'm going to talk about the Challenger explosion. This one's a bit of a real Debbie Downer. So in 1986, the Challenger space shuttle exploded in the United States. Unfortunately, this was a very well televised event. They were sending up a school teacher, so a lot of schools were watching this. I remember very vividly, I was 13 years old when this happened, and I can remember being at home at lunch hour and watching this happen. Anyways, so the issue they had with this flight was something called, it was a problem with their O-rings. And O-rings, if you know what propane cylinder gas tanks look like, they've got a little rubber connector that keeps the gas from leaking out. And with space travel, it can be quite costly to do testing. They do testing, but then they also do they do an analysis after the flights have happened. And so what they did was they would go collect the booster rockets that had been jettisoned from the space shuttle, and they would take a look at what had happened. And so what they did was they took a look at these incidents of O-ring failures, and they were looking to see if the O-rings had worn away or broken during, the hard work of sort of lifting the space shuttle off the ground. It's fairly big. There's a lot of energy that's released, and they were looking to see if the O-rings were surviving this, because they knew that if the O-rings failed, they were going to have this gas leak and it would be problematic. They actually had 2 O-rings at each space, so that the first one could fail, the second one would hold on. So all of these cases, there's 1 O-ring failure that they discovered. And you'll see that I basically put a 1 for had a failure and a 0 for did not have a failure. And you can sort of get a hint there that as it's getting colder, that's in degrees Fahrenheit at the bottom. As it's getting colder, you're starting to see a few more O-ring failures. But they looked at this and they didn't really see much to it. So they said, well, they just dismissed it. Now, in my future readings of this, since I put this in the presentation, I found out that some of the lower level engineers had a lot of concern about this space shuttle flight, but there was sort of a management issue there where they weren't listening to their junior staff. But that's a whole another problem that isn't statistics. They also looked, sometimes they had multiple O-ring failures because there were more than one place on the jettison booster rockets where there would be O-rings. So they took a look at this as well. And again, we can see this sort of, I don't know, almost parabola happening. And so if you try to fit this with a straight line, it's going to look something like this. This isn't exactly what the straight line model would look like, but it's approximately what would happen. So it doesn't really make any sense. They looked at this and they're like, well, okay, there's nothing really happening here. But what they had, and they didn't realize it, was they had something called the logistic curve, which is modeling zeros and ones. Normally we use straight line regression if we're modeling something like age by height or years of experience working with income or something like that, something that has a continuous linear pattern to it, which failure and success definitely is not linear. So it turned out this is what it should have looked like. There was this huge curve, and what happened was they launched the space shuttle that day at about 35 degrees Fahrenheit, so 1 degree Celsius above freezing or 2 degrees above freezing, and it was guaranteed to fail almost. There was a 96% chance failure rate for these O-rings. And so if they listened to sort of their junior staff who had modeled this a bit differently than the other people had, they would see that this was almost a guaranteed fail. So this is sort of a really like a Debbie Downer, upsetting one, but we see that not understanding the math that you're studying, not understanding the statistics behind the data can cause some real problems. So this one sort of speaks better to some analysis presentations that I think might be coming up. But yeah, it's sort of it's a bad math where unfortunately 7 people died. So yeah, let's move on. All right, imputation. This is my first one with sort of a subtitle to it. It says, with great power comes great responsibility. And normally in my class, I would ask my students who they think this comes from, because a lot of people give this quote to Uncle Ben from the Spider-Man series, but actually it was by a French playwright named Voltaire. And so that's where this comes from. Why do I say with great power comes great responsibility? Imputation is one of the most powerful tools we have when it comes to surveys. This can, a mistake in your imputation rules can completely change your data set. So we're going to have a look at this in detail. So now for imputation, we moved on. So the stuff that I was teaching before was all about frame. It was all about drawing our sample. It was all about how we were going to select stuff. This is now afterwards. So this is after the magic happens. This is after collection. And I think, yeah. There's two types of possible non-response that we can have. So there's total non-response, where all or almost all of the data from the sample genomes are missing, or there's partial non-response, where information is available for only some items. So items should probably say maybe some questions or some variables. And the effect of this is that it's going to reduce our sample size. So if we selected, say, 1,000 dwellings and only 900 of them replied, then this is effectively reducing our sample size. Our sample went down from 900 from 1,000. And it has the possibility to introduce non-response bias. And this can be really problematic. And we're going to talk about that as well in a little bit. So for non-response, ideally we would have no non-response. But we end up having non-response. So how do we avoid this at Statistics Canada? So publicity, we send out letters for all of our surveys. By sending out a letter, it gives the respondents the opportunity to read the material and to know why we're going to contact them. So whether it be an interviewer coming in person, which is a lot rarer, or it may be that they're getting an email to say, we want you to conduct a survey, or they might be getting a phone call. If they have a letter that they've received beforehand, we find that this greatly, what's the right word? Greatly improves our response rate, because it's given the people the time to sort of read into this, and it may have given them time to look into it too. So they may question, like, is the labor force survey real? And then they can Google it and see that, okay, yes, Statistics Canada is in the field collecting, so this makes sense. Incentive to answer, this is an interesting one. Statistics Canada currently doesn't do this and never has in the past. I think from research, what we've seen is that it sort of introduces a slight bias, that if we give a small payment, such as say $5 or $10, what this will do is it will bias it towards people who are motivated by $5 or $10. So it would motivate to maybe lower income. It motivated towards students. So Statistics Canada just has never done this. Pilot studies, we do this all the time. So we'll do it for a small geographical area to see what's causing non-response. Very good interviewer training. We do some of this is Statistics Canada, maybe not enough, but it's something that we recognize as being very important when we send our interviewers out, that the better trained they are, the higher the response rate will be. We'll have long periods of collections. So some of our surveys are in the field for a week, and some of them are in the field for 2 weeks, and some of them are in the field for even longer. Prior to COVID, when people might travel a lot, if the collection period was only 1 week and the respondents were away for a week, then you were guaranteed not to get them. We also do respondent follow-up. We have at least 2 levels of interviewers. I see I got a question. I'm just going to finish this thought. So we have at least 2 levels of interviewers. So for example, we have our, what we call interviewers, and we have senior interviewers, or non-response conversion experts. And they will follow up with people that have originally said no. And I've seen some very good interviewers. I've never seen anyone labeled as a non-response conversion sort of expert, but it's incredible to see them work. To me, it's magical to have this collection happen. I think I mentioned this in a previous presentation where I said, if you have a response rate of 60%, it means that 3 out of every 5 people that you've contacted have agreed to do your survey, and which I find just amazing. But most people would say, oh, 60% response rate, that's really low. So that's what we do. So the question is, so would you not recommend incentives for official statistics surveys? If you're currently using incentives and it's working for you, then I would say continue. Statistics Canada, this is something we've started looking into. I've seen presentations on some of the field work they've done on it. And one of the things they would ask is, they would ask them, how much of an incentive would it take? And I think part of the problem for Statistics Canada is it's just too costly. So when we do labor force survey, we contact 60,000 people a month. So if we gave if we gave a $10 incentive to 60,000 people a month, I mean, that's 600,000. That'd be $7.2 million a year just for the incentives for labor force surveys. So I think maybe part of the problem for Statistics Canada as well is that it's just impossible in scale. So I'm not sure if the official Statistics Canada recommendation would be not to do it, but there's definitely some pitfalls, and it might be worth following up with some research on the internet to see what the advantages and disadvantages of that are. Or you could always contact Tracy and find out through Prask what it is. So the follow-up question is, but you mentioned this can bias your demographic respondents. Is there any documentation I can share on this? I haven't seen it. I've only heard it sort of anecdotally from other methodologists. So it might be worth doing a quick Google search on this, and you might be able to find something. And again, if not, you can follow up with Tracy. That'll be my standard answer, Tracy, just to follow up with you. Okay, so we've conducted a survey. We're done. The field staff have come back. At Statistics Canada, there are an incredible number of codes that can be associated with an active interview. So when the questionnaires are out in the field, they'll have a status that we keep looking back at. And so the status might be something like never contacted, never attempted, busy phone number, no one home, partial complete, soft refusal, which is when we'll send back another interviewer. But by the time it comes back to us, and when it's final, when there's no more interviews that are going to happen, this is the data set. There's basically 4 different categories that we split this up into. And so we're going to look at these today. So a fully complete questionnaire is a questionnaire that's had all of the questions answered. And it doesn't mean that every single question is answered. It means that every single path has been followed properly. So for example, if it's a question about pregnancy and the person responded that they're male, then they won't be asked any of the questions on in the health survey. They won't be asked any questions on pregnancy. It's not that the survey isn't fully complete. It's just that that path of questions wasn't applicable to that person. A partially complete is when we are actually missing answers. So again, I mentioned this earlier. This can happen when an interview stops halfway through, which an interview gets interrupted. It could be that the respondent just gets tired of answering the questions and hangs up on us if it's a telephone interview. And sometimes it's just question-wise. So for example, they may refuse to answer their income, but are happy to answer any other questions that we have. So partial completes can come from many different ways. We can have complete non-response. So complete non-response is there have been no answers or very few answers. So for example, if we have 2 or 3 questions that have been answered, so for example, let's say we call a household and we ask them, do you live in the target area? Let's say it's the city of Ottawa where Tracy and I live. Do you live in the city of Ottawa? Yes. Is this a private resident? Yes. Okay, we're going to ask you a few questions on, municipal garbage service. Do you put out your blue bin and black bin? And they're like, oh, I'm not. Yeah, okay, I put out my blue bin, which is for plastic recycling. And then the next question is, how many garbage bags you put out every 2 weeks? And they're like, no, I'm not doing this. And they hang up. We've only have like 4 questions answered. It's completely useless to us to keep that information. So we would just flag that as completely as a complete non-response. Out of scope, which is super scary to us. Out of scopes are those that have answered or were selected to do the survey, but weren't eligible. So for example, if we are doing a resident survey on garbage collection, like I just mentioned, if we happen to contact a business, then they'd be out of scope. If we have a phone number for someone who we think lives in Ottawa, but they've moved to say Toronto, which is sort of 400 kilometers away, then they wouldn't be eligible for the survey anymore either. But they would be in our, they may be in our sample still. So the out of scopes are really, really bad news. If we're doing analysis, if we're looking at an unadjusted data set and we will say, okay, well, let's do analysis. If we haven't done any treatment to the data at all, we would only have the fully completes to work with. That's all we'd be able to work with. But we'd really like to include the partially completes. So what we're going to do is for the partially completes, for those that have given us enough information that we're willing to keep it. So we set a minimum number of questions that have to be answered. And sometimes there are questions that must be answered for them to be included. When we do that, we're going to impute the rest of the answers, or potentially it's one of the strategies we use of which to impute the values. If we have complete non-response, but we know that there was an in-scope unit, then we'll reweight it. And if it's out of scope, then we'll drop it. So that's how we deal with this stuff. Okay, so what are edits and imputations? So an edit identifies missing or data or erroneous data, and then the imputation corrects it. So the relationship between edit and imputation is the edit detects the problem, and then it'll blank out the value, and then the imputation program or the imputation process you're using will come in and fill in an answer. So a lot of times you'll hear people colloquially say, I edited, I have a respondent who's listed as male who, just gave birth. I edited it to female. Well, what they really did was the edit found the fact that male is erroneous, removed the value, and then they use imputation to replace the value with female. That being said, I mean, we are quite forgiving when people say they edit values to something. So when we look at different types of edits, so one of the types of edits we have to look at is something called a validity edit. So is the value they're trying to answer valid? So, if someone tries to put that they're 214 years old, or if they try to enter the letter E for age, like for their age, this capture screen should reject it. So if we're doing some sort of computer questionnaire, the computer can right away reject these answers. Whereas if it's a paper interview, if it's a paper one and it's being self-reported by the respondent, you can't stop them from putting 214 years old because it doesn't work. And then there's also these capture edits, which is they will look to see the relationship between questions and skips. So like I keep saying, we don't want pregnant men. And then imputation, we replace these blanks or invalid or inconsistent data with valid and consistent data. Okay, so let's take a look at some methods of imputation. So there's deterministic imputation and there's stochastic imputation. So deterministic imputation, given the respondent's data, there's only one possible value. So as soon as we see the data for have given birth, and then we may see some variables that talk about the birthing process, the birth weight of the baby and stuff, we know right away that this is a female. And so it's determined right away it has to be this. Or we may have something where we say, if age is less than 15, then employment income must be 0. So even if the kid has a job, we may not want to capture it in our survey, and we may force that to be an imputed value of 0. So if the edits go through and find a 12-year-old who's got an income, salaried income of, I don't know, say $6,000 a year, the system will go in and say, no, we don't want that. And then the deterministic imputation will set that value to 0. With stochastic imputation, there's some randomness added to it. And so this means that if you keep hitting the imputation button, which we always frown upon, then you will get a different answer each time, or potentially get a different answer each time. So different types of deterministic imputation. So deductive imputation, so that's one possible value based on related items, which is what I talked about with pregnant men. Mean imputation, so it uses valid responses from other records to calculate the means. So the mean being average. So for example, if we have, to make this very simple, if we're looking at income and we have males and females, you could say that we'll take the average income for males and impute any value for male that's missing with that. Or you could say that we'll do, and then the average value for females. You can do ratio or regression, so you can build any sort of model you want. So you may have other variables available to you, and you can model it that way. So you can do a regression and saying, based on education, based on age, based on sex, you may give different possible values for income in that case. Sequential hot deck and sequential cold deck. It's interesting. I always like to bring this up with my class because this is so antiquated now that no one knows what it is. So hot deck imputation and cold deck imputation. Hot deck imputation uses data that is coming from the same data set. So the imputed values come from the data set that we're looking to impute data from. And cold deck imputation will find an external data, or will use an external data set to impute values. So the reason this is called hot deck and cold deck is this comes from the old punch card machines. So they used to take every questionnaire, they would feed it through these punch card machines or Scantron machines. And at the end, if they were missing one, they would just randomly take one or sequentially take one out of the pile and put it through the machine again. So if the data set had just run through the machine, it would be hot. And if they used something like a data set from the previous month and they took one off the shelf, it would go through cold because it hadn't just been through the machine. And in 5 or 10 years, exactly no one who's working will have any idea what hot and cold deck imputation means. Now, nearest neighbor imputation, this one's one of the most common ones in Statistics Canada. So it finds the donor closest to the missing value in terms of matching items. We don't literally mean neighbor in the sense of they live down the street. We mean neighbor as in we've set a parameter of characteristics and they're nearest that way. I think I'm going to talk about this a bit later, so I'm going to not speak on it now, but this one's really important. Another one that's not on this list that should be here is historic imputation. So for example, if we're doing a monthly survey, maybe a survey of some business, we can look at the previous month's results and then just use that going forward. Or if we want to use a ratio regression estimation, we could say last month, this company that it was coal mining, they made X number of thousands of dollars. That market has gone up 2% in the past month. They will take last month's value, multiply it by 1.02 to add the 2%, and that'll be this month's estimate of what they probably would have done if they'd answered the survey. Okay, so for stochastic imputation, the one where we don't always want to get the same answer, what they do is so you can do imputation with a random residual. This is super common. So if you want to do imputation by mean, like by average, you always give the same answer. And what they do is to make it look more real, they just perturb the data a little bit. So I have a horrible example of this from early in my career. In fact, when I very first started working at Statistics Canada in the late 1900s, I worked on a survey that dealt with longitudinal income. And so every month, what they would do is they would ask, this was a very long survey, they would ask, do you have this source of income? Yes or no? And if they answered yes, they would ask them how much it was. And there was, I think, 80 different types of income that they could possibly ask them about. And one morning I got to work and I was a super junior staff. And the director and his senior analyst, they were both in my office waiting for me when I got there. And I thought this was really exciting. I was like, oh, wow, I've got these very senior staff coming to visit me. And they said, we want to know why every teenage girl on the file has exactly the same dividend income. And I thought to myself, okay, this is bad news. And I instantly had an idea that, okay, the problem is it's imputation. And so I told them I'd get back to them in sort of, 15, 20 minutes. And I sat down to look at it. And sure enough, what had happened was, and we're going to talk about this a bit later, but I'd like to sort of start on it now, is we had there was only, so every teenage girl, every person was asked, do you have dividend income? Only 15 of them said they had dividend income. And so of these 15, you asked them, okay, what value, how much money did you make on dividend income? One of them responded that they made $8,000 in dividend income. And then the other 14 said, I don't know how much dividend income I made. So when I went to run the imputation, which was all automated, it looked for a donor, a nearest neighbor donor. So it found another female teenager, and it just imputed 8,000 for every single one of them. And so it was actually kind of good that this got caught, because we don't want to work with small donor pools, and I'm going to talk about that a bit later. But it right away set off this flag for the analyst that when we look at female teenage dividend income, it was all exactly the same. And luckily they were forgiving about this. I still have a job at Statistics Canada, but that was sort of a big mistake, a small mistake that I made with imputation early in my career. Okay, so let's talk here about this donor imputation. So the nearest neighbor stuff. So what is a donor? So what we're trying to do is we're trying to replace missing values. And maybe I should take a step back and say, I'm not really convinced that I've really said that's what imputation is all about. Imputation is about replacing these missing values. So for example, if we're missing income, we want to try to replace this value. We need to find a donor, someone who can give the income value to this person. So how do we find these donors? We divide the file into two, so donors and recipients. So the donors will have income plus all the variables we're going to match on. The recipients will have some subset of this, and then we'll try to make these matches. And then we want to find potential donors by matching recipients to potential donors on certain items. So gender or sex. Here, revenue is one of the variables we've used to match, but if that's the one we're looking for, it's going to be difficult, and education. And the matching items have to be linked to these items so that we can compute them. So one of the questions we have to ask ourselves is, should all of the recipients' missing items come from one donor? And the answer here is maybe. Sometimes it's nice if you find a nice match for someone else in the variables that you're using to find a donor. It's good to just put them all together. So the example I constantly like to go back to is this one about giving birth. If you talk about the height, they're called length, the length of the baby and the weight of the baby, it's probably good to impute those two values from the same donor. So you don't want to end up with a really long baby for the length of the baby and a really small weight coming from a different donor. So for all the characteristics about the birth itself, you may want to put those and compartmentalize them into one group so that we'll select that all from one donor. Now, can a donor be used multiple times? Yes. I talked about this in the last slide where I made the mistake of having 8 people imputed from the same donor. That in itself isn't bad. That can happen, but it's something that you're going to want to keep track of. There's really, you usually like to set a maximum number of times a donor can be used, and you'll set a flag, and you should set a flag in your program so that you can see this in the outputs. But there's nothing wrong with the donor being used multiple times. It could be that you've got a very small population, like teenage girls with dividend income, or it could be there's some other reason that this donor is being used multiple times. But if it's a big enough data set, this shouldn't be a problem. Okay, so let's take a quick look at an example here. Oh, actually, no, I want to go back to this. We don't just divide the file in 2, we actually divide it in 3. But donor and recipient are the 2 major ones, but the donors are also then split in 2 different groups. Donors that we accept and donors that we reject. And donors that we reject are donors with outlier data. So for example, if we have someone with a very high income, we may not want them in our donor pool because it may skew the data by including them as a donor if they get used too frequently. So let's take a look at this. So here is here's farms again. So we see the number of acres. We see the total expenses. We see the expenses on fertilizer here. And then at the end, we see this ratio of fertilizer to total cost. And so we're going to try to impute 5, 9, and 10. But for this little example I'm going to give, we're really just going to try to impute for farm number 5. Okay, so if we take a look at the average, the mean of expenses on fertilizer, all we have to do is take the sum of all of the fertilizers, which is the sum of those 7 values, then divide it by 7, and we see that the average value is 6,586. So for units 5, 9, and 10, we would just impute 6,586. And what this does is it keeps one of our most important variables, or one of our most important statistics, which is average. It will leave it the same. So by imputing this way, it doesn't change the average from those that have given us a value. And hopefully people are seeing an issue with this already, which I'm going to talk about later. Another way to do this, so we can look for nearest neighbor based on acres. So farm number 5 has 300 acres. And the nearest neighbor by size is actually farm number 9, which has 330 acres. But the problem is number 9 also needs to be imputed. It's also missing the value for expenses on fertilizers. So we have to look for the nearest neighbor that has the same value. So the nearest neighbor here would be farm number 1 with 350 acres. We see that the expense on fertilizer is 2,000. And then we would just impute the value for farm number 5 with 2,000. Then we would repeat the same process with farm number 9 and farm number 10. We see that farm number 10 is really big. So based strictly on acres, it would be imputed from farm number 8. Here we look at by if we happen to know the total expenses. So it may be that farm number 5 said, here's my total expenses for the year. And we asked how much was on fertilizer. They said we don't keep track of that, so we don't know. So we know that they spent 400,000. And if we look to find nearest neighbor based on expenses, again, here farm number 10 would be the closest one, but farm number 10 needs to be imputed, so it's excluded. We pick up farm number 1. So farm number 1 is the closest one. We'd say, okay, it had 2,000. So we're going to put 2,000 there. We could also model this and say that farm number 1 is 6% bigger than farm number 5 based on total expenses. So we could add 6% to the fertilizer expenditures, which would be another $120. So we could do $21.20 there if we wanted. Or we could do, so ratio of expenses. So here they're looking more at that last column. But they do this using the total expenses and total fertilizer. So they see that of the farms that responded, they did $46,000 in total expenses on fertilizer. They divided this by 1.7 million, which is the total expenses. And then they said, okay, let's do this as a model. And they said, okay, so we'll take whatever the ratio of expenses is multiplied by the total expenses for this farm. And this gives us 10,567. So by these 4 different methods, we see that by the average, by the mean, it's 6,586. By nearest neighbor, we get 2,000. And by the ratio of expenses on fertilizer and total expenses, we get 10,567. I'm going to pause here for a second. Does anybody want to mention in the chat what's potentially wrong with this data set? What issues I'm having? Why are the estimates of my imputation coming out with such different values? So farm number 8 has this huge value of 40,000. And if we take a look at the ratio of fertilizers there, farm number 8 has spent 7.3% of its total expenses are on fertilizer, where the other ones are all like 0.6, 0.5, 0.7. And so it could be, there's a couple of potential problems here. One is it may be shifted over by 1 decimal place. It could be that this farm meant to enter 4,000, which would then make its ratio of fertilizer 0.7. It could be that's a totally different type of farm. So it could be a type of farm that it has a certain type of crop that requires a lot of fertilizer. So it could just be there's a different type of farm. Either way, I would suggest, I would force you, suggest is the right word. I would suggest that you leave this value out. And if we take a look at the solutions, if we leave this outlier out, if we take a look at the average value now, it becomes 1,016. And then the nearest neighbor doesn't change, it's still at 2,000. And if we look at the ratio of expenses on fertilizer to total expenses, we get 2,040. So they're all hovering around the same value. Now, we see that for method number 1, I gave 2 possible answers to what the average value is here. I said 1,016 or 1,220. $40,000 has definitely been spotted as an outlier. But there's something else to be concerned about here that a lot of people don't think about, and that is farm number 6. Farm number 6 claimed to spend 0 on fertilizer. We have to sort of be concerned, is this true? Or did they put 0 because they don't know? Or maybe worse, did the computer system default it to 0 because they didn't put it in? Now, I don't think it would default it to 0 because we see that in our 3 that need to be imputed, there's no value. But did this farm really spend 0? This may be an outlier on the small side. And so you may want to exclude, you may want to say of farms that have claimed fertilizer expenses and make your donor pool based on that. So there's all sorts of rules we have to be concerned of. What about nearest using the nearest neighbor by acres and then looking at the ratio of fertilizer to total? Yeah, that's also a very good one. So that's sort of what I hinted at. Nearest neighbor by, so nearest neighbor by acres got us farm number 1. So what the question is, what if we use nearest neighbor to find the neighbor, but then we model based on that? So like I said, farm number 1, we could say that farm number 1 has 16% more acres than farm number 5. So 50 over 300 is about 16%. And we could say, okay, let's reduce the expense on fertilizer by 16%. There's all sorts of ways we can model this. And this really comes down to sometimes we want to have subject matter experts that are dealing with it. Perhaps they know the type of farm and they know the type of fertilizer. Imputation being such a powerful tool, it's important to have good survey, I can't get my word right, subject matter experts to look at this stuff. So we don't want to do this haphazardly. We want people that know what they're doing to be working with our data. Okay. What do we have to think about here? So there's a bunch of things that we want to monitor. So the number of items being imputed, this is very important. So we want, as part of our output after the imputation process, we want to have all these variables coming out. We want to be able to look at this piece of paper and say, is there anything problematic with the imputation that was just done? And unfortunately, when I gave that example of when I was a junior employee, the imputation process was so big and there were so many outputs coming out that I'm going to say I wasn't told to watch for certain things, as opposed to I just didn't look for certain things. I'm going to let myself off the hook. So the number of items have been imputed, the number of times an item has been imputed and which method was used, the number of potential donors for each item in the case of donor imputation, and a list of failed imputations. And I'm going to talk about all these a little bit here. So the number of items imputed. So part of the issue here is that we want to look at, let's say income has been imputed, I don't know, 20% of the time. This wouldn't surprise me, because a lot of people, if you ask them how much money they make, they will politely or less than politely decline to answer that question. Whereas if you're asking something like, what is the average number of times you don't eat at home in a week, and the imputation rate was 20% there, I'd be concerned that something went wrong with the edits. So there may be something, the number of times that something's edited is also going to be a problem here. So we also want to look at edit flags. This happened, I worked with another methodologist, and those of you from Guyana may remember him, Hugh Goff. He was down there teaching this course with me. He also did work in Africa, and obviously before they went to these countries, they would try to get a lot of work done ahead of time. And he told me once that they were doing a, I think it was a census of building structures in the country, and they were trying to help the country with this. And so they looked at some potential edits and that they should look at. And one of them was, if the walls were made of straw, it almost sounds like the Three Little Pigs. If the walls were made of straw and mud and the roofs were made of concrete, then there must be something wrong, because this doesn't, to Hugh and the team at Statistics Canada, this didn't seem reasonable that you could have straw and mud siding or walls with a concrete roof. And it turned out when they went and spoke to the experts in this country, this was actually a very common building strategy there. So if they had implemented this, they would have ended up eliminating all of these right answers and imputing values that for questions that have been properly answered. So we have to take a look at this. The number of potential donors for each item in the imputation. This goes back to my problem with the teenage girls again. And a list of failed imputations. If you have a failed imputation, meaning you found no donor, this means that this value will still be blank on the data set. And this will be really problematic if you're trying to do analysis and you have values that aren't there. And I don't mean zero, I mean they aren't there. When you try to take an average, if you try to do a lot of mathematical stuff in computer systems and they don't have values, a lot of them will often crash. So to wrap up, I just want to do a quick comparison between imputation and reweighting, because a lot of people find, I get this comment quite frequently in the course that I teach, that people aren't comfortable with the idea of imputation. So when people show up at Statistics Canada, I would argue that nearly 100% of them have never heard of imputation before in their life. This isn't something that they teach at Canadian universities. Tracy, you can correct me if I'm wrong, but I'm almost certain that I didn't learn anything about imputation when I was taking statistics. It's too specific to surveys and data sets like this. And I think that I can't even imagine what course they would have taught me that in. So they don't teach us this. So when you show up to work at Statistics Canada, they say, okay, someone refused their income, we're just going to take this value from somewhere else. People are like, this feels uncomfortable to me. You're taking the value that someone else gave, and then you're just going to slot it in there. So this is just a quick little demonstration of what reweighting and imputation does. So in this data set, which is just an example, it's really small, there's only 3 respondents. So we have these 2 males and this 1 female. And the female is obviously older and better educated based on our data. She's making a lot more money. And so we look at it and say, okay, we need to impute the income for this male. And so there's a couple of strategies we can use. Okay, so one of them is we can say, let's find a nearest neighbor. We have someone who's got the same gender, they're both males, they're the same education, they're roughly the same age, they're not quite the same age. So they say, you know what, we'll take this value 35,000 that the other male made, we'll slot this in, and we'll say this male made $35,000 as well. So that's one way we can do it. If we want to reweight it though, what we would do is, so I've added this column survey weight. No, we had the column survey weight. So originally, these 3 people were supposed to represent a total of 300 people. In the end, we still want them to represent 300 people. So what we do is we say, let's move the weights. I'm going to talk about weighting next week, but I need this for this example today. We're going to shift the weights on these 2 other respondents. We'll say, okay, we'll give the male a weight of 150 and we'll give the female the weight of 150. But what this kind of does is it says that by reweighting, you're effectively saying that that first person becomes a male female who's got a high school and PhD education. They're 26 and 54 and they have an income of 80,000. So we've taken the average there. It's sort of it. If we have this information, available to us that, you know, the males on our survey tend to make, that have that education and are around that age, make about 35,000. It's to our benefit to use this if it's available to us. And so to me, reweighting is the last thing you should be doing. And the first thing you should be doing is you should be trying to impute. We have values for similar people. We'll just use that. And to the people that have problems with this, and some, you know, when I'm teaching this face to face, I can sort of see, or when I'm teaching in person, I can see in their face when they're still uncomfortable with this idea of imputation. We impute, the fact that we're doing a survey, we impute automatically. So if we select, let's say, every 10th person to do an interview, by assigning a survey weight of 10 to that person, we're saying there's 9 other people that we're never going to talk to, that we're going to use this person's result to give us our final answer, and we're going to slot those values in anyway. So imputation is just reweighting within a certain category is a way to look at it. The other thing too is by showing an unfortunately small data set, imagine this was, instead of 3, imagine this was 3,000 and we only had to impute a handful. There may be a whole bunch of different males with high school education in their 20s that their program could pick from. And if it picks just one, it might end with this 35,000, or it could get 50,000, or it could get any other value that someone has given. So it will give us an answer that is possible. And then if we were to do this over and over again, it would get the average. Or if you want to impute by average, which is a possibility, we've seen this, you could just take the average of all males who have high school education that are in their 20s and slot that value in there. And then for each age, education, and age group, age, gender, education, we would have a different value that would get slotted in. So it'd be saying young males with high school education tend to make this, older females with PhDs tend to make this, and we can impute that way. So that's basically what I want to say.